Okay, so here we are again. Before I talk for 40 minutes straight, what questions do you guys have about anything?
Are the lab submissions due tomorrow evening?
Yes, so for Professor Beth's sections, go with whatever she said. For my section, it's not tomorrow evening. I think I made it due Thursday evening. Although frankly, I would be flexible on that. The Thursday labs I would like by Tuesday, but the Tuesday lab by Thursday, since you're turning it in online, you could turn it in by probably Friday. It'd be fine.
Okay, thank you.
Of course. What other questions? Okay. Okay, so let me remind you that, no, I don't want to do that. Let's just move forward. So we're talking about chapter 6 today. Actually, today is the first day of chapter 6. There are 3 videos posted for that, introducing basically everything for the chapter. So today is the introduction. Tomorrow is basically just more examples. So there's not much new tomorrow. So let me go quickly over the basics. All right, again, this is a reminder. I presume that you have watched the pre-lecture videos for this. So if this feels like it's going fast, it's because I assume that you've already seen it in my voice, right? Basically the same words I'm about to say. So the idea is this: we're talking about impulse. Slide down. Impulse. Impulse is just a way to capture the net effect of a force on an object, right? So if an object experiences a force.
Sorry to interrupt, but we can't see what you're writing.
Why not? All you can see is me.
Here's an interesting example.
That's great. You know what that was? That was my own video. Hey, I could just play my video straight into the lecture. Why can't you see what I was doing? Oh.
It just says scratch 15.
It does, and that's what my page says, and it has the things that I wrote on it. Why is it not updating? Ah, technology. I love you. I hate you. While we're waiting, the reason I have this video, no, come on. This is the video, one of the videos for tomorrow. I already have a comment. Molly asked if I want to be friends. And I don't know. I'll think about it. I'll think about it. I'm not going to be pressured into friending someone that. Okay. So what am I doing? We're almost there. Okay. Thank you for telling me that you couldn't see what I was doing. There, impulse. So a force acting on an object for some time, right? So for some delta t, leads to a change in its motion, right? And we know that. We know that a force, a net force on an object leads to an acceleration, and an acceleration over some time leads to a change in velocity and a change in position. But we're trying to capture like the net effect of this. So the average force acting over some time, we define that as impulse. All right. And in fact, this is a vector equation. So the force has a direction. So impulse also has direction. We also said if you one of the reasons for thinking about force average is if you looked at force versus time, right? So the particular kind of interaction we're thinking about for this chapter is a collision, meaning two objects hit each other. So they're in contact for some small amount of time and then they leave. So the initial force before they're touching is 0, and the final force after they're not touching is 0. But during the collision, I expect it to be, you know, some maybe more regularly shaped thing than that. But depending on what the objects are, it could be anything. It could be more like a Gaussian, like a smooth curve. It could be more like a triangle. It could be like a trapezoid. So this is just an example of some force versus time. And it turns out the area of this thing is the impulse. So area equals impulse. That's actually a more official definition for this, is the area of a force versus time curve. So we could say area of force versus time. And I did some math with this in the pre-lecture video, where F average is just A average times delta t, and A average is delta V over delta t. So that's that F average you could just replace with m times delta V over delta t. And then the over delta t and this delta t go away, and you end up with this change in the quantity mv, right? So we could call that delta m times v. And if we define a new quantity, momentum, p, as m times v, then, nope, what I want to do is just erase this. Then I could call impulse a change in momentum. Okay, so we have these three definitions for impulse, and often what we end up doing is choosing two of them in a problem to solve the problem. So let's do an example. So we're going to go back to the chapter 6 lecture handout. Nope, that's the wrong folder. Here, chapter 6 lecture handout. I think I just want to do this one. So example number 3 here says a pool ball hits the bumper of a pool table at 35 degrees and it rebounds at the same angle. The question is, what was the impulse on the ball from the table? What was the impulse on the ball from the table? So I know that impulse J is delta P, right? And again, that's a vector equation, and that vectorness is going to matter here. So the impulse J is P final minus P initial. So I could do that in a vector way. I have P final and P initial vectors here. So let's do that. Right, so again, I'll say vector-wise. It's supposed to be a W. Not much better of a W, but that's fine. So I'm just doing vector math here. P final minus P initial. P final looks kind of like this. That's P final. Really having issues. And minus P initial kind of looks like this. Minus P initial. Right? It's just P initial just pointing the opposite direction. So like that. Okay, and the vector sum of those, right? So P final plus negative P initial is J. So it just points like this. That's the impulse. All right, so that's not what this is numerically yet, but it's going to help us conceptualize this. So what we notice here is the y direction. If we call this y, we call this x. The y direction for the momentum is not changing. Only the x direction of the momentum is changing. And remember, momentum is basically just velocity weighted by mass. So only the x component of the velocity is changing, which means ax should be non-zero, should be some number, but ay should be 0, right? Which means that the net force needs to be pointing to the right. That needs to be what this force is. And force leads to impulse, because the other definition for impulse is F average times delta t. Average times delta t. And that's vector as well. So it kind of makes sense that the impulse should point to the right because the force needs to point to the right. Okay, all of that is to say, it makes sense that the impulse points to the right. And it's not just going to be the strict difference of the momenta, right? I need to consider just the x components of the momenta. Okay, so let me pause and ask, how do you feel about that so far?
So is there no, or AY is 0 because the arrow, like the momentum J, is pointing in the right direction only, not going up?
Yep.
Okay.
Yeah, in fact, we could prove that to ourselves by asking, we could say, you could break J into Jx and Jy, because J is a vector, and Jy would simply be the difference of P final Y and P initial Y. But what we notice here, in fact, this is great because this segues right into the next thing. If I break these into components, there's P initial X, and here's P initial Y, and here's P final Y and P final X. The Y directions, those arrows are the same thing, right? If I could draw better. But the X direction arrows, those are the ones that are changing. And that's how I know that the impulse is just in the X direction and not in the Y direction. Does that make sense?
Yeah.
Fabulous. Okay, so we've determined kind of in a gut sense way that J only points in the X direction. So all I need to think about are the X components. So that's the next bit here. So J, really it's J sub X, is going to be P final X minus P initial X. So I need to know what those components are. And I remember the definition for P is M times V. And in fact, P sub X is going to be M times V sub X. Is that the way I want to go? It's one way we could go. I need to determine, though, where is this 35 degrees? And the 35 degrees is as measured to the table, so that must be this angle right here. That's the 35. So it looks like the X component is actually the opposite, right? So X is actually sine. Do you see that? If I'm careful, here's my right triangle. And the X side is actually opposite, and X is opposite is sine. Okay, let's move back to black. Okay, so we could just fill this in the next line. It should be M times V final in the X direction minus M times V initial in the X direction. And we just said the X component here is P times, well, yeah, V times sine theta. So M times V times sine theta. You know what? I want to be careful here, because again, let me just solve these bits off to the side, because look at this. P initial X, that points to the left, right? Correct. My dad was a driver's ed teacher in the summers for years and years, and he learned when a student asks, you know, is this correct? The answer is correct, not right, because he had a student in a left turn lane say, I'm turning left, and he said right, and they turned right from the left turn lane, and he survived to tell the tale. Okay, So there's that little tidbit, and it'll show up in the YouTube video, so it's preserved for all time. Maybe Molly will want to like that comment too. So P initial X should be negative mv sine theta. Do you guys buy that? Again, the mv is the length of the momentum. Sine theta just gives me the x component, and the negative sign is because it's pointing to the left. By the same token, P final x is positive mv sine theta. And actually, I can plug those now in over here. So, in fact, I could have plugged it in the previous line. Let's do that, since I have power to erase things. Okay, so P final x was m times v times sine theta minus negative mv sine theta. So in total, I should have 2 mv sine theta. Why do I have 2 equal signs? It's confusing. So I could plug in numbers. 2 times, what are the masses here? 165 grams, so that's 0.165 grams times the velocity is 1.5 meters per second times sine of 35 degrees. And what I get for this is 0.28, 0.28, and the units here, kilograms meter per second. I would like to put a big box around it, but I can't change pages. Okay, so 2 things. I have not yet mentioned in this video, or in this meeting, that the unit for momentum, also for impulse, is kilogram meters per second. Again, it was in the pre-lecture videos. Also, our answer was positive, which makes a lot of sense because the momentum change is to the right? And the average force is to the right. There's no way for this bumper to apply a force to the left unless it's like sticky. So let me ask, does this make sense? What questions do you have about this?
Is there ever a time when, so is P initial always going to be a negative, so it'll be minus a negative?
No, I could have drawn this entire problem backwards. There's a problem I already worked. We could have set up this problem and said, what if it does this and bounces off this way? Then P initial x would be positive. Does that make sense?
Yes.
Cool. What other questions do you guys have? This idea of delta P and the sign of delta P is kind of important, and sometimes it can be tricky. But I find drawing a picture and drawing the before and after and figuring out the components is probably the best way to figure it out. So let me talk about a couple things. Really, what I want to talk about for the rest of this session is some conceptual ideas. Because I worked out all of the example problems I had in the videos, right, in the pre-lecture videos for today and for tomorrow. But there are a lot of conceptual bits that need to show up. And some of them I did talk about in one of the videos, but let me go back and mention those. So we talked about impulse, we talked about momentum. So let's do this. Let's have 2 eggs. That doesn't look like an egg. That doesn't look like, that's an ostrich egg. Sure, okay, 2 eggs. Or a ambivalent robot. No, 2 eggs dropped from the same height and falling to the ground, right? One of them, oh, come on. It's trying. I win. Okay. Okay. So, and we're back. So 2 eggs fall from the same height. One of them just hits the ground, and the other one falls in, I don't know, a box of feathers. How do you draw feathers? Those are Big Bird's feathers. It's molting, I guess. Oh, come on. Come back. I'm still drawing feathers. So while this is loading, let me set up the conceptual question. So the question is, do I expect a different result when the 2 land? One hits the linoleum in the kitchen, the other one lands in a box of feathers. Do I expect a different result for the 2?
Yes.
Yes. Yeah, clearly this guy's gonna break and this guy is safe. What was the, so let's call this case 1 and case 2. What was the change in momentum for these 2? Meaning, does one of them have a bigger change in momentum than the other?
Is momentum the same thing as acceleration?
No. So let me ask, let me clarify the question. So the change in momentum at the very end of the motion, right? So as they fall, they accelerate the same way, right? Up until they hit the box. One hits the box, one hits the floor. But the change in momentum from this motion, from just before hitting and coming to rest, I expect that to be the same for each of these, right? Because as they accelerate toward the ground, so here's draw an intermediate step. At this point, they should have the same speed, right? There's some speed, there's some speed. And their final, so we could call that initial, just before the collision, and their final speeds are both 0. So they should have the same, this is maybe not the best way to do it, but I don't care. They should have the same change in momentum, which means they have the same impulse. They receive the same impulse from the floor. But clearly something is different about this interaction, right? And the difference comes in the average force. The average force and the time of the interaction, right? Because remember, J equals F average times delta T. So they have the same impulse, right? They receive the same impulse from the floor, but the box of feathers increases the amount of time that it takes the egg to stop, right? The box of feathers increases the amount of time it takes the egg to stop. So I could say for this one, it's a larger delta T and it's a smaller delta T for the floor, which means the egg that hit the floor should feel a larger average force, and the egg that hit the box of feathers should feel a smaller average force. You guys buy this? All I see are pictures of people. I don't see heads nodding.
Yes.
Fabulous. Okay, awesome. Yeah, so there are lots of times that we have a collision with a fixed delta P, meaning a fixed impulse. Anytime you have something that's moving and then coming to rest, you can modulate the average force by modulating delta T. This is what airbags do, right? This part of physics is the examples I have are so violent. The first conservation of momentum question involves a handgun and recoil velocity, but it's just the examples that come to mind for me. So maybe that says something bad about me. So when a car hits something and comes to rest, right? Why does your head stop moving? Well, there has to be a force on it, right? And in the absence of anything else, it's your neck that stops your head, right? Or, the steering wheel, heaven forbid. But when your body stops because of your seatbelt, your head stops at the end of your head moving forward, right? That's how you get like whiplash, right? But if something pushing against you before your head hits the end of its range of motion, right? Meaning an airbag, that can increase the amount of time it takes your head to stop and decrease the average force on your neck, really. Does that make sense?
Yes.
Another example is crumple zones in a car. So years and years and years ago, cars were made like steel boxes. And so when a car hits, another car or an embankment or something, it kind of just jolted to a stop. Nowadays, cars are built to crumple. So they experience a lot more damage, but it takes them longer to stop. And because it takes them longer to stop, delta T is larger, the average force on the car is smaller. Right? So the car is built to crumple like a tin can. Right? That's a feature, not a flaw. Let me give you another example. Let me pause though. Are there questions? Okay. So here's another example. I think this is probably a quiz question. Let's have two balls, same mass, but one is rubber. That is not how you spell rubber. Mostly how you spell rubber. And one is clay. Right? So the rubber ball falls and bounces. The clay ball falls and sticks to the ground. The question is, which of these two objects felt a bigger impulse? Which of these two objects felt a bigger impulse from the ground? Well, this seems tricky. Or it seems like, well, isn't this pretty similar to before, where we had these two eggs hit and the impulse was the same, right? Well, the impulse for these two eggs was the same because they both came to rest, right? So the delta P for each of them was the same. You had a P pointed down before and a 0 momentum afterward. But here, the rubber ball has a momentum pointing down before and a momentum pointing up after. And the clay ball has a momentum pointing down. It's the same momentum pointing down, but momentum final is 0. So it feels like maybe the clay ball feels a bigger impulse because it deforms. But frankly, the rubber ball deforms as well. It's just elastic. And so you get that energy back because it stored it as elastic potential, kind of like a spring. And then it it gave you that energy back as momentum going the other direction. Whereas the clay ball deformed and stayed deformed. So you lost that energy, the work that it took to deform the clay. So the clay actually feels a smaller impulse, where the rubber ball feels a bigger impulse. You guys buy that?
Yes.
Cool. Cool. Okay. I talked about that one. So the other big idea in this chapter is conservation of momentum. Momentum has a conservation law, just like energy had a conservation law. We said mechanical energy was not conserved anytime there was friction. Yeah. Momentum is conserved as long as there are no external forces, but friction can be a part of it because conservation of momentum does not rely on conservation of energy. We'll talk more about that tomorrow. So anytime, we'll say, if there are only internal forces. And what I mean by an internal force, good grief, I can't. Let me slow down. What I mean is forces that are between objects in the system, right? And I think I defined this in one of the videos. A system is just a collection of objects. So if I have two objects bounce off of each other, so there's one, there's two, and then later they've bounced off of each other. There was some internal force, right? This like normal force between them. And even if they slide against each other and there's some frictional force, as long as that's the only force acting on these objects, momentum of the system is conserved. So I would say P1 initial plus P2 initial equals P1 final plus P2 final. And in fact, that's a vector equation. So that's true in both the X and Y directions. And again, I have posted several examples like that. But conservation of momentum is useful for lots of things. Let's talk about a rocket. How do you draw a rocket? Oh, I don't know. Sure. There's my rocket. How do rockets take off? I don't know. I think you need red for that, right? Maybe some yellow. Sound effects mandatory. Okay, so what is happening when the rocket is firing its thruster downward? Well, it's feeling some force upward, right? This thrust. And it's tempting to say, oh, it's pushing off of the ground. And I would say to that, it feels that way, but it's not pushing off of the ground. Because if it were pushing off of the ground, it would be like you jumping off of the ground, right? And once you leave the ground, once the rocket is no longer touching the ground, it would be in free fall and it would fall back to Earth, just like when you jump off of the ground. What's happening here is the rocket is literally throwing mass downward, right? It's carrying some fuel and it's burning the fuel and it's ejecting. Let's get rid of the ground. No. There, now the ground is gone. So it's ejecting mass this way. So this is the momentum. This is P for the exhaust. And that matches with P for the rocket. So this is a conservation of momentum question. The thrust that we get is because you're literally throwing mass downward. It's the same thing as in empty space, right? So imagine you're in space. How do you move? Well, you can't like pull on things because maybe there's nothing around you. So if I want to move, let's actually draw it. If I want to move this way, I need to throw something that way. It's just conservation of momentum. So if I had like a wrench, how do you draw a wrench? Nope. How do you not draw a wrench? Ah, nailed it. Right, so if I had a wrench, this is my before picture. Can't write with an eraser. Sorry, I was looking at the time. That was the reason that one was illegible. Everything else is just legitimately my fault. Be fair. Gosh, I swear. Okay, the after picture would be the wrench going this way and me getting smaller. No, me going this way. My initial momentum is 0 and the final system momentum is 0. I gain momentum to the right by throwing something to the left. That's in essence, how every rocket works, right? So you're throwing lots and lots of tiny masses, right? Like the gas from the exhaust. You're throwing lots of tiny things very fast. Let's see, questions so far? Okay. So let me suggest that you check out the example problems for this, the pre-lecture videos for today, if you haven't already, and the pre-lecture videos for tomorrow, because that contains lots more explanation of what I've just been going through and several example problems. So I'll ask again, are there any questions? Okay. So take a look at those problems. If you have questions that crop up, feel free to come by office hours, send me an email, or when I ask tomorrow, if you have any questions, you could ask them then too. That's totally cool. Because if you have a question about something, it's very likely that someone else also has that question. Cool. Okay, if there's nothing else, let's call it a day. Megan, do you have a question?
No.
Okay, I saw you unmute yourself. Maybe you were just getting ready to say goodbye.
Yeah.
Okay. Goodbye, Megan.
Bye.
And goodbye the rest of you. All right, have a good night. I'll see some of you now and some of you tomorrow in discussion.